Hi all, good morning. And today in today lecture we are going to learn about memory management. But where memory management? Where are we managing memory? So basically, we will learn this term in terms of operating system, how the operating system manages the memory, and how the memory allocation is being done when a program or a process is run into the memory. So the basic functionality of OS, OS has a lot of functionality, but here the functionality of OS that we are going to learn about is about allocating and deallocating memory to the processes. Allocating and deallocating, both are opposite terms. So allocating and deallocating memory to the processes. Okay. So this is the functionality possessed by the OS. So OS has the work of allocating and deallocating memory to the various process. Now why OS comes into picture? So the goal is for the proper memory management. Okay, or you can say efficient utilization of memory. So when we want to utilize the memory efficiently, efficient utilization of memory, for this we need to follow this. Just a minute, give me some time. Okay, let me have it. Okay, so I'm back. Right, so we were talking about goal, and goal refers to efficient utilization of memory. And of course, we will learn later that we need to minimize internal and external fragmentation. Now what is internal and external fragmentation, that we will see later. So this is one thing, external fragmentation. Okay, so first is better utilization of memory, and second is minimizing internal and external fragmentation. So this is the goal of using the OS to manage the memory. Now let's see how we are managing, how the OS is managing memory. So basically, we will display the memory like a chunk of. Here we have the different bytes are being stored. So byte is nothing but a group of bits, that is 8 bits equal to 1 byte. So memory can be either be addressed as byte addressable or word addressable. So basically memory, if this is a memory, it can be represented in two ways. Okay, so first is byte addressable, and second one is bit addressable. Okay, so one is byte addressable, second is bit addressable. Now what is this byte addressable and bit addressable? So when we address memory, we can say that this entire chunk of memory is something called 512 kilobyte. So this is byte, and kilo means 10 to power 3. Okay, so this is called byte addressable because we are representing memory, the capacity of memory in terms of bytes. Okay, so this is byte addressable. Now what is word addressable? If we say this memory is 512 kilo word, now we are addressing the memory, the capacity of memory in terms of word, kilowords. That is call it as, I'm so sorry, it shouldn't be bit addressable, it should be word addressable. Okay, I'm sorry for that if I have been pronouncing bit as a word as bit, but it should be word addressable. So if we say the capacity of memory is 512 kilowords, then we are representing memory as a word addressable. So basically, this memory capacity, in terms of capacity, if we are talking, if we say this memory has a capacity of 512 kilobytes, then it is a byte addressable memory because we are addressing the memory in terms of byte. And if we say the memory is has a capacity of 512 kilowords, then we are representing the memory in terms of word. It is said to be word addressable memory. Okay, so in this way we represent memory. Now let me illustrate what is this word or byte addressable part. So let's first of all we need to have this like if we say 2 squared, it is 4, right? When we say 2q, it is 8. When we say 2 4, it is 2 raised to the power 4, that is 16. 2 raised to the power 5 is 32. And 2 raised to the power 7 is 128. Okay, right? Similarly, 2 raised to power 8 is 256, 2 raised to power 9 is 512, 2 raised to the power 10 is 1024, and 2 raised to the power 11 is 2048, and so on. Okay, but here when we terms about memory, we have said that it is 512 kilobyte, then it means 512 into 2 raised to the power 10 into byte. So this kilo doesn't means 10 to the power 3, it means 2 raised to the power 10. Okay, so kilo means 2 raised to the power 10. If we talk about mega, it is 2 raised to the power 20. If we talk about giga, it is 2 raised to the power 30. If we talk about tera, it is 2 raised to the power 40, and so on. So whenever we are saying 512 kb, that means 512 into 2 raised to the power 10 byte. Okay, so this kilo means 2 raised to the power 10. That I want to clarify from this. Okay, so let's see what does a word means and how do we measure the capacity of memory. So already I have drawn this diagram. I'm just redrawing it so as we could see what I'm trying to say. So this is a chunk of memory. Now if we want to determine the capacity of memory, let's say this memory is byte addressable. Okay, so these are the block in which we are keeping our data. So let's say we just name this block as 0, 1, 2, 3, 4, 5, 6, 7. Let's say this is an additional. Let's okay, let's remove it only. It's not working. Just a second. Oh, okay. Now, let's say we just have this section. It is divided into 8 section, and in each block we are storing our data. So let's say here we can store 16 bits in each of this. So 16 bits can be 0, 1, 0, any random sequence of bits. So all together we can store 16 bits here, right? So if we want to represent this memory, and let's say we have divided this memory into 8 blocks. So this 8 blocks would be addressed something like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 100, 101, 110, and 111. Now why we are representing in terms of binary? Because in computer we don't have this representation. We represent everything in terms of binary. So this signifies the block number, and this signifies, this 16 bit signifies how many bits we can store here. So if someone asks to calculate the capacity of this entire memory, let's say this is a ram, and if we want to calculate the capacity of this, so what we'll do, in each block we are storing 16 bits. 16 bits is equal to how many byte? 16 upon 8, that is 2 byte. Okay, so in each we are storing 2 byte. And how many sections are there, how many divisions are there? So altogether they are 8 divisions. That is multiplied by 8. So we can say 2 into 2 power 3 that is 2 power 4, 2 raised to the power 4. So it is altogether 2 raised to the power 4 is how much? 16 byte. Okay, so this will be the capacity of this memory chunk. How we calculated? With the number of bits we can store here, that is 16 bit, and 16 bit is equal to 2 byte. So in each we can store 2 byte of data, and how many 2 byte of data we can store, we can calculate with this number. So it is how many sections we have divided this memory into. So we have divided it into 8 section. So it is 8 into 2 byte, and that is equal to 16 byte, right? So this way we can calculate the memory. Now see here, we have used the term byte, so definitely it is a byte addressable memory. Had it been the word, then it will be a word addressable memory. So that is the basic difference between how we are representing the memory, okay, in terms of word addressable or byte addressable, right? Now there are some questions that I would like to solve here. So let's say we have a system, and a system is consisting of 64 megaword, that is its capacity, and each word has a size of 512 bits. So there is a system, certain memory or RAM or chunk of memory. Now it has 64 megaword, okay, 64 megaword, and each word size is 512 bits. So total, this 64 megaword is total words, okay, total words, and each word having size this. Then if someone asks what is the capacity of memory, and also in byte, what is the capacity of memory in byte? So if this is the question, first you need to be sure that if we are referring to word, then definitely this memory is word addressable, okay. And when it is a word addressable memory, then this 64 mega word is the number of word we can store in this memory. So number of word, total number of word that we can store in this memory is 64 mega word. That is 64 into 2 raised to the power 20, right? So this much word we can store in this memory. So this much word we can store means total number of word that could be present is this. And we are saying that each word has a size of 512 bits. If we convert that into byte, then it will be how much byte? 512 divided upon 8, and this is how much? Let's divide like this: 2 raised to power 9 and 2 raised to the power 3, that is 2 raised to the power 6. So it is 2 raised to the power 6 byte. Each word is 2 raised to the power 6 byte, and there are altogether this much word. So definitely if we calculate the capacity, then the capacity will be total number of word into each word size, that is 2 raised to the power 6. This we can also convert in 2 raised to the power 6, 2 raised to the power 20, and then 2 raised to the power 6. So altogether is 12, and 12 is 32, 2 raised to the power 32, and that is equal to 4 GB. Okay, so the capacity of this whole memory is 4 GB in terms of bytes. Okay, this is the answer, right? So this way you can calculate the capacity of the memory. Okay, let's see one other question, that there is a system. If we talk about system, it's just the memory chip or any RAM chip. So again, there is a system which has 128 gigawords. 128 gigawords. Now again, it is a word addressable memory. Word means total number of word that we can store in this memory. Okay, so this system has 128 gigawords. This is the number of words we can store. Okay, and if we talk about that, each word having the size of 256 byte. Okay, now this word size has been given into byte. So when such question comes, you need to visualize this like this way. So this is the system. Okay, and in this system there can be 128 giga word. So each this block is in terms of word, so this is one word. Okay, and such how many words are there? 0, 1, 2, and so on up to 127. Okay, that's how it becomes 128, right? So you can visualize this as this way, that there are altogether 128 giga, all 28 128 words, and each this slot is one word, and in this one word it refers to 256 byte. So that this instead of this one word we can store 256 byte here. So either say one word or 256 byte, right? So there are altogether this much word and each word having this much size. So what is the capacity? Obviously it is 128 multiplied times 256 byte, right? It is as simple as that. That is the capacity. Okay. Now we already have seen that we can represent this in the form of 2 raised to the power 7. We can represent this in 2 raised to the power 8. And yeah, this is 128 gigawords. Sorry, I'm really sorry, it's not 128, it is 128 gigawords. So giga refers to 2 raised to the power 30. Okay, so it shouldn't be like this. Actually, we need to convert the total number of word here. That is 2 raised to the power 7 into 2 raised to the power 30. That is altogether 2 raised to the power 37. And altogether it's 128. Okay, fine. So 2 raised to the power 37 words. So it will be 0. Let me just erase what I have done. Okay. So it is 0, 1, 2, 3, so on up to 2 raised to the power 37 minus 1. Okay, so we can multiply it by 2 raised to the power 37 multiplied times 2 raised to power 8, and that is equal to 2 raised to power 45. Okay, and that is equal to 32 terabyte. Tera refers to 2 raised to power 40, and then it's 32 TB. So this is the capacity of this entire memory. Okay, so is that clear right now how we calculate the capacity of memory in terms of byte and in terms of word? There is one more question. If just for patience, let's see this question. So again, we have a system. System can be a RAM chip or any such system where we have the storage capacity. So it has 32 binary bits, 32 binary bits. It's simply just bits only, just illustration. 32 binary bits are used to represent all the words of memory. And each word, one word size is equal to 32 bits. Then what is the capacity of this memory? Now see, this question is a little bit twisted. Now here you have been given word size as 32 bits, that is equal to 32 upon 8, that is equal to 4 byte. So you have the word size, but now you don't have the number of words. Okay, you don't have the number of words. So if this is your memory, which is divided into word, and each word having size of 4 byte. Okay, so 4 byte and so on, but you need total number of words. Now here there's it is saying that 32 binary bits are used to represent all words of memory. So one word can be represented by 32 bits. Okay, so altogether 32 bits. So total number of words, how many total number of words could be if one word can be represented by 32 bits? So let's simplify this. If one word can be represented by 2 bits, let's say 00 is used to represent one word, so how many altogether word combination can be formed? 01, 10, 11. So altogether the number of words can be formed as 4. Okay, if 2 bits are used to represent one word, so there can be 4 different word. Similar way, so what we have done here, 2 raised to the power 2, that is 4. Similar way, if we have 32 bits to represent one word, then altogether how many words could be formed? 2 raised to the power 32. So now we have got that the total number of words could be 2 raised to the power 32, and each word having size of 4 byte. Then from here we can calculate the capacity as 2 raised to the power 32 into 4 byte, and that is equal to 2 raised to the power 32 into 2 raised to the power 2, and that is equal to, if we multiply this, 2 raised to the power 32 into 2 raised to the power 2, 2 raised to the power 34, and either we can write it like this, or we can simply write it like 16 gigabyte. So our capacity of the system will be 16 gigabyte. Now, is that clear? From these three questions, I suppose that anyway, whatever be the question in terms of calculating the capacity of memory, you would be able to calculate the capacity of this memory. Okay, so this is all about how we are representing memory, how to calculate the capacity, what are the two addressing forms in which we address memory. Now let's talk about how we can implement a memory. Like, we have one RAM chip, and how we can utilize that RAM chip to organize the main memory, or because memory consists of various RAM chips, right? And we when you look at any memory system inside your computer, there will be several RAM chip constituting whatever we just discussed, like this. It can be a RAM chip or it can be a memory. So how this memory is implemented within your system, that is what we are going to see now. So the topic is RAM chip implementation. RAM chip implementation. Well, I suppose we can cover this part in the next video, or we can see it here because it is similar to what we have discussed now. So let's go with the flow so that we can conclude this in this series only. So RAM chip implementation is being done to support the memory system. Okay, so let's say you might have learnt about RAM and ROM, and that is what we are going to see now. So let's say that you have a RAM chip, and you want to make a memory or organize a RAM chip in such a way that you can create a main memory of some size. So let's say the RAM chip size is 128 byte. Okay, now this 128 byte means one altogether 128 byte of data can be stored on this RAM chip. Okay, now you need to create a memory or organize a memory, let's say the main memory only. Okay, we need to organize the main memory, which is a capacity of, let's say, 128 byte. Okay, sorry, 128 byte is the size of this RAM, right? So let's say we want to create a main memory of capacity 16 KB. Okay, so we have to organize this RAM chip in such a way that we can create a main memory of size 16 KB. Now, the question comes, how many RAM chips are required to create this main memory capacity of 16 KB, and how you are going to organize all this RAM chip inside the main memory? So, it's little diagrammatical. So, first question is, how many RAM chips are required? Okay, so if you want to create a memory, so if you we have to find out how many RAM chips are required. So we have a memory of 16 KB. So that is equal to 2 raised to the power 4 into 2 raised to the power 10. into 1 byte. Okay, so this is 16 16 kb upon, we have this 128 byte, so 2 raised to the power 10 into 1 byte, right? Now this you can conclude like this will be cancelled, and this can be 2 raised to the power 3, and altogether it will be 2 raised to the power 7, and that is 128 ram chips could be required. Like this way we can conclude this part. Okay, but the question is, how we are going to organize this 128 ram chip to create this memory of 16 kb. Okay, so basically first part is solved, but the second part is how to organize, right? So what we will do, we have a ram chip of 128 byte. Let's see how this ram chip is organized. So we have something like this in this way. So let's say this is our ram chip, so on up to this. So this 128 represents the number of this row, and this byte represent the data. So data in terms of bits. So it will be 0, 1, 2, so on up to how much? 7. Okay, so 7 bits altogether of 8 bits of data one row can hold. And altogether, how many rows will be there? So it will be 0, 1, 2, so on up to 127. Okay, so altogether 128 rows, and each row holding 8 bits of data. So this is the case of RAM, that is 128 byte holding RAM. Now this RAM is now being organized into a memory of 16 kb, and altogether how many RAMs are required? How many we have already calculated, that is 128. So 128 RAMs are required. So how we are going to organize this RAM? So 128 RAMs are required, and each RAM holding 128 bit of data, sorry, byte of data, 128 byte of data each RAM holding, and we have to constitute a memory of 16 kb. Now you see here, if we divide like this, 16k means 2 raised to the power 4 into 2 raised to the power 10, that is 2 raised to the power 14, and this is byte, that is 2 raised to the power 8. Okay, so we can constitute it like each RAM holding 128 byte of memory, and there are 128 RAM, so we can do it like this. Like we have this RAM, each RAM holding 128 byte of data, each RAM holding 128 byte of data. And how many altogether this RAM are? 0, 1, 2, and so on up to 127, because we have 128 RAM and each RAM holding 128. So this way we can constitute the memory. So altogether this will be 16 kb memory. And here we have altogether 127 rows. So we can have a decoder here, 7 into 2 raised to the power 7 decoder, decoding all these lines, something like that. So this can be the main memory structure based on the RAM capacity and total number of RAMs required, right? So this way we can organize our memory. Now let's see one more question where it will be more clarified of how we are organizing the memory system based upon the RAM chip constituents. So let's say we have a memory RAM chip of size, let's say the number of RAM chips required we need to have is 256 into 1 bit. Sorry, it is the capacity of RAM, and we require a memory of capacity, let's say 32 MB. We can divide it as 2 raised to the power 5 into 2 raised to the power 30. No, 2 raised to the power 2 into 2 raised to the power 30 or 20. Sorry. My bad. It will be not this. So it will be something coming like 2 raised to the power 5 into 2 raised to the power 20 byte. That is 2 raised to the power 25 byte. Okay. And it will be something like 2 raised to the power 25 into 8 bit. Now see why we are dividing like this, that because the RAM capacity comes in terms of bit. So the RAM would be constituting like something like this. So there will be altogether 256 rows, right? 0, 1, 2 up to 2 to the power 8 minus 1, and each row will be storing 1 bit only, like this way. So this is the way the RAM is constituted, and we have to create a memory of capacity 2 raised to the power 25 into 8 bit, because 1 byte is 8 bit. Why we are doing this? Because we are just to calculate the number of RAM required. What we are doing, we are dividing the memory size with this RAM size, that is 2 raised to the power 8 into 1 bit. So things has to be in the same format, because here is 1 bit, so this byte has to be converted into bit. Okay, so now dividing the number of rows, that is how much it will be, I think 7 17. Okay, and it will be 2 raised to the power 3. So total number of RAMs required is 2 raised to the power 17 into 2 raised to the power 3. Now this 2 raised to the power 3 is each word strength, or you can say that each block will contain this much of bits, and this is the number of rows, and this is each row constituents, each row size. Okay, so this is the total number of RAMs. So this can be multiplied and it will give us 1M. So number of RAMs required is 1M. But how will this RAM will be constituted to organize this into the main memory is something coming from this part, that is the organization part. So number of rows will be 2 raised to the power 7. Since this memory is not bit addressable, it is byte addressable. So 2 raised to the power 3 is something called 8 byte, right? Or let's say 8 bit only, not byte, because we have this thing in bit. Okay, so it will be 8 bit. So 2 raised to the power 3 is 8 bit, and that is equal to 1 byte. Okay, so but the number of rows will be 2 raised to the power 17. So 1 0 1 2 so on up to 2 raised to the power 17 minus 1, and this will be the memory. And in each row we are holding how many byte? 1 byte, or let's say 8 bit. So 0 1 2 3 so on up to 7. So in this way it is being stored, right? So altogether 2 raised to the power 17 rows will be there, and each row it will be holding 1 byte. So this is the main memory organization. Okay, now the third question could be how many number of decoders are required. So you see here, I can't scroll here, but let's see. If there are 2 raised to the power 17 rows, so the decoder, whatever we are constituting, it will contain altogether 2 raised to the power 17 rows. So we can say that it will be 17 into 2 raised to the power 17 rows. Okay, so altogether it will be decoder size will be 17 into 2 raised to the power 17, because the number of rows is this. Okay, so Yeah, that's it. I mean, this way we can constitute the main memory. So this is what I want to show, that based upon how the RAM is there, we have to organize the memory accordingly. There's one more question saying that the RAM chip size is 512 into 2 bit. Now, just see this part. RAM, we are making the main memory from this RAM chip. So RAM chip size is 512 in 2 bit. This means that inside the RAM, the number of rows is 512, 2 raised to the power 9. And each row can hold the data of 2 bit. Okay. Now, if we want to make a memory of capacity, let's say 16 MB. So what does this means? This means that we are having 2 raised to the power 4 into 2 raised to the power 20 into 1 byte. So this is the number of this should be the number of rows in the memory, and each row should be constituting this 1 byte, that is 8 bit of data. Each row should contain. So why we are dividing this in such a way that we have this much rows inside the RAM and this much rows are being required for the memory. Okay, so if we want to calculate the number of RAM required, so we can have like this: 512 is the number of rows for each RAM, and each RAM is holding 2 bit of data. And what we want 2 raised to the power 4 into 2 raised to the power 20 rows, and each row holding 8 bit of data. So in this way, how many RAM are required? So it is something like 2 raised to the power 24 into 2 raised to the power 3 upon 2 raised to the power 9 into 2. Sorry, it is 2 raised to the power 9. Don't read it as 29. Okay, so this will be getting cancelled, like 2 raised to the power 15, and this is 2 raised to the power 2. So now we have something called number of RAMs required is 2 raised to the power 15 into each row should be constituting of 2 raised to the power 2 bit of data. Now this is bit. Okay, so 2 raised to the power 15 into 4. So this is one row should be constituting of 4 bit of data. Now, this is not byte addressable. This is bit addressable. If you want to make it to byte addressable, definitely you have to take one, two twos from here and constitute. But this is the way we are going to organize that's what I wanted to show. So now we have this memory, and each row there are altogether 250 2 raised to the power 15 rows. So 0 1 2 and so on up to 2 raised to the power 15 minus 1, and each row will be having a 4 bit of data, like 0 1 2 3. Okay, so in each row 4 bits could be stored, and to process this we need to have a decoder of 15 into 2 raised to the power 15 uh, a decoder to us to address all these address lines. So in this way the memory is going to be organized. So this is how we are going to divide the RAM to constitute to organize the main memory structure. Okay, I hope this is clear. From this example, this would be more clear. I think it is the last example that we are discussing. So we will conclude after this uh, last topic. So this is one structure of main memory. So let's say we want to make a main memory of capacity. Let's say main memory capacity would be something called 4 MB. Okay, so 4 MB would be the main memory capacity, and it has to be built with DRAM chip. Here we are using DRAM chip, and this DRAM chip would be 1M into 1 bit. Now again, sorry, I'm writing this so many wrong things here. Okay, so this 1 bit. Okay, now this 1 RAM is equal to 2 raised to the power 20 rows, and 1 bit is the data size, that is each RAM each DRAM would be having 2 raised to the power 20 rows and each row holding 1 bit data. And we want the memory capacity of 4M, that is 2 raised to the power 2 into 2 raised to the power 20 rows into each row holding 2 raised to the power 3 bit data. Okay, so this is for in bit. So now we need to have how many DRAM chips would be required. So it is something 2 raised to the power 22 rows are required and each row holding 2 raised to the power 3 bit of data, divided upon how many RAM rows are there, 2 raised to the power 20 into 1 bit. Okay, that is equal to 2 raised to the power 0. Okay, so this is what each row will be consisting of, and this is the number of rows required. Okay, so this will be coming as 2 raised to the power 2 and this will be coming as 2 raised to the power 3, obviously. So now we have the DRAM is equal to 2 raised to the power 5, that is 32. So total 32 DRAM are required. Now how this DRAM is going to be organized? So this DRAM is going to be organized like something like this. So altogether how many rows? 2 raised to the power 2, that is 4 rows. So it will be 0, 1, 2, 3, and in each row we are holding 8 bit data. So it is something up to 7, right? So there are 7 bits each row. Sorry, not 7. This there are altogether 8 bit. Each row would be holding, and altogether there will be 4 rows. And to address this 4 rows, we have 2 into 2 to the power 2 decoder, right? So the decoder size will be 2 into 4 decoder is required, and memory would be organized like this. Now if the question comes that so this is the capacity and organization of memory. Now if the question comes that each chip has 1k, or each DRAM chip has 1k of rows of cell with 1k cells in each row, and time taken to refresh is 100 nanosecond. Okay, so, what is the time required to perform one refresh operation on all the cells in the memory unit? So, basically, we need to calculate the total number of time. So, what it is saying that in each DRAM chip, I already have drawn the DRAM organization. Okay, not so it is something like the DRAM size is 1M into 1 bit. Okay, and each DRAM has 1k of rows of cell with 1k cells in each row. Okay, so it is constituting of something like this. There are all together 1k row, 0, 1, 2, so on up to 2 to the power 10 minus 1. So altogether 1k of rows, and each row is having 1k cells. So 0, 1, and so on up to 2 power 10 cells. Okay, so there are altogether 1k columns, you can say something like this. Okay, so 1k cells in each row, and time taken for refreshing means reading or writing, accessing all this operation. Time taken for single refresh of operation, single refresh operation time is 100 nanosecond for each, for the entire RAM. This way is 100 a nanosecond. So if we want to perform this single refresh operation onto the main memory, okay, so what is the time required? That is the question. Okay, so if we say this in terms of memory, so we have how many we can conclude like something like it is 100 nanosecond, right? So altogether how many the time required to perform one refresh or operation in all the cells in the memory unit. So if we see the memory unit, it is something like this. These are the RAM organization, and this is each bit of data. This is the data bit, and we have to calculate the total time taken for this entire operation. Okay, so altogether, what is the memory size for the RAM unit is 2 raised to the power for the RAM is 2 raised to the power 10 into 2 raised to the power 10, that is 2 raised to the power 20. Okay, so this 2 raised to the power 20 into how many bits are there, how many bits one row can hold, that is 2 raised to the power 2 into 2 raised to the power 3, and altogether is 2 raised to the power 25, and then it has to be multiplied by 100 nanosecond, because here we are calculating the altogether total number of rows, right? So basically what I'm doing is, let me show you. So for one RAM consisting of 2 raised to the power 10 into 2 raised to the power 10, we have for 2 raised to the power 20 cells. There are 2 raised to the power 20 cells in each RAM. Okay, and this will be holding data equal to how many thing, like 2 raised to the power 2 into 2 raised to the power 3, right? So altogether 2 raised to the power 25 cells are there, and each operation, like each one single refresh operation requires 100 nanosecond. So we are multiplying this by this, and this goes to 3200 into 2 raised to the power 20 nanosecond will be the answer. Okay, we'll see next about how we are calculating. Let's conclude this lecture by now, because I think it is too late to start another lecture. So just focus on to this, how we are organizing the memory and all and everything like that. We'll start up the next topic in the next lecture. So that's all for this lecture. Thank you very much for watching. Let's conclude it here.